So I've got a, are you going to talk over?
Yeah.
Ah.
Okay, so welcome everyone to today's complex system seminar. So today our speaker will be via Zoom, and some of us.
Deborah, you're muted.
Oh, so it's not captain.
I don't know.
It's going to be a bit messy.
It was working fine when you were muted.
Oh, sorry. Okay. I'll shut up. Mute yourself again. And hi, Shannon.
So it's my great pleasure to introduce our speaker today, Professor Michael Tse from the Department of Electrical Engineering, City University of Hong Kong. I believe Michael collaborate for a long days now. In fact, in my PhD, I read that paper on complex research of musical compositions through complex networks. So that was inspiring for me. But today is not going to talk about compositions, but modeling of coronavirus transmission. So I'll go there, Michael, to start.
Yes.
Okay, thank you very much.
All right. So can you all hear me?
Yep, we can hear you fine.
Okay. All right. Yeah. So it's a pleasure being here in Perth today. Not physically though, and I would like to thank Michael for organizing the seminar and for inviting. So let me just do the sharing screen now. Okay. So, all right, okay. So in the next 45 minutes or so, I'll be explaining to you some of the work that we've been doing in the past 6 months, I guess. Actually, we started looking or collecting data since January, early this year, and then constructing models for analysis and prediction of the pandemic progression of COVID-19. And in fact, my interest started back in 2003. I think Michael was the person who introduced me to this area back in 2003, when we had a fairly serious problem at that time in Hong Kong. The SARS virus was affecting something like less than 2,000 people, but it's a lot less severe, I mean, compared to what we have this year. But we actually started building model at that time, and I will explain in the next few minutes some of the background, and then I'll move on to introducing the model that I use for analysis and prediction of COVID-19 in the past few months. So I guess these early facts, and most of you are quite familiar with some of this background. Actually, COVID-19 started in December. Officially, it is known to have started in December, in the middle of December in Wuhan, which is a very centrally located city in China. And then the outbreak actually become fairly serious around the time when, just about 1 week before the Chinese New Year. So we reckon that the so-called spring rush, which is about 20 to 30 days surrounding the Chinese New Year day, in that particular period of time, you will see millions of people in China were actually traveling from city to city. And Wuhan being the center, you know, with a lot of traffic hubs and transportation, as well as a lot of universities, factories. You can imagine a lot of people were actually traveling in and out of Wuhan during that time. And this is actually an earlier chart showing what we call nowadays the first wave. In fact, we are now having second and third waves of outbreaks. You will see from here, basically looking at 25th of January, all the way down here. This is the Chinese New Year time. So you can see about 1 week, about 10 days before that, the traffic becomes very heavy, actually started to become very heavy in China. So this is actually the background. I think most of you are familiar with that now. So let me just show you the Hong Kong situation. First wave, quite lucky. We basically was not very much affected during the first wave for reasons that the government didn't really want to mention about. In fact, if you look at the calendar back in December 2019, we actually had 25 Eason Chan, which is one of the very popular pop singers in Hong Kong. There are 25 concerts scheduled in Hong Kong Coliseum, and then 23 shows for Andy Lau, and all canceled actually. And also many big events were canceled during that time, not because of COVID-19, and we didn't have any idea of COVID-19 at that time. And it was because of these social events. So some of you might know that we have a lot of protests in the past 1 year, anti-government protests, basically. Fairly peaceful, many of them are. Actually, so that actually saved us for the first wave. But then the second wave, you see starting around early March, there are quite a lot of overseas students coming back from UK and the United States. And that actually triggered quite a bit of, during that time, there are communities spreading from early March all the way to April. Lan Kwai Fong is one of the biggest group which actually accounted for something like 10% of the total number of infected individuals. And Lan Kwai Fong is actually a restaurant area and pub and bar area in Hong Kong. Oh, actually, one more thing. We became famous because we had one of the first dogs in the world diagnosed and confirmed with COVID-19. Now we are having the third wave beginning. So that was the second wave I mentioned earlier. The third wave basically started something like 2 weeks ago, and it is now believed to be caused by a fraud policy, basically, by the Hong Kong government. Back on June 9th, the government allowed something like 70,000 people entering Hong Kong borders without quarantine and basically unchecked. And you can guess, why we allow 70,000 people. Actually most tourists or actually there's no tourists nowadays. There are people who are actually coming back from overseas because of work or study, but everyone needs to be quarantined for 14 days. But this 70,000 people basically exempted. And then taxi drivers, restaurants, party clusters accounted for something like 50 to 60% of the infected cases. And this 2 weeks, in fact, all restaurants are closed in Hong Kong after 6 o'clock. And it seems that today and the day before, we have something like 80 cases, lower than what we had like 3 or 4 days before. We had something like more than 100 every day for about 12 days. Anyway, let's get back to the China situation. spring rush. One of the reasons that triggered us to work on the travel data is because we believe that the spring rush is one of the key factors that contribute to the rapid and fairly, severe outbreak during the Chinese New Year time. And so Wuhan, where is it? Is right in the middle of China. And it actually has the busiest high-speed rail traffic hub in China. So it's basically connecting almost every city throughout China. And it has a population of 11 million. And is a center of higher education, manufacturing plants, industry, and business. And so we started to look at how we could integrate data collected from transportation. And it turns out to be very difficult because it actually involves railway or airlines and so on. And then we found there's a very, very useful cell phone app called Baidu Migration. For those of you who know this, basically it is a mobile app sort of system. Basically, it actually records everyone's movement around the country. So in other words, when you turn on your Baidu, basically you are being monitored in a way. So wherever you go, the system actually knows where you are. And so the Baidu actually has this. So let me just explain this particular page here. On the x-axis here is the Baidu migration strength, which is basically an indicative value of the sort of volume of traffic going into a particular city. Okay, so from Wuhan. So Baidu actually can tell you roughly how many people are actually going into, for example, Shanghai, or how many people are leaving a particular city. So we actually add up all the traffic going from Wuhan to a particular city and then plot it on the x-axis. And the y-axis is the number of infected cases recorded for that particular city. And you can see that the number of cases is roughly proportional to the Baidu migration strength. So what we are saying here is that when there are more people coming from Wuhan to a city, that particular city will normally have a higher number of infected cases. That is back in February 2020. So the data. So this is the mobile app-based human migration tracking data system, extremely popular in China. So basically apparently everyone uses it. So it actually provides indicative inflow and outflow volume of travelers between cities. And we can actually collect data quite freely from Baidu website every day. So my postdoc is actually working on data collection, and that's why he's busy every day collecting data. So this is basically what we have in the first step. We are collecting data. We have been collecting data since January 2020 for 367 cities in China. And then we extended it to Japan, United States, Iran, Italy, Spain, UK, and Australia recently. And we actually have limited access in some cases, but for example, in the case of United States, we are able to get monthly or weekly data similar to Baidu. It's basically a database of intercity travel. So we have some indicative figures showing, the sort of traffic or movement of people from city to city. This is actually an interesting piece of information. If you compare this year, that's 2020, with last year, that's 2019, there's a significant difference here. So this particular chart on up here is the inflow to Wuhan. And because of the lockdown, you can see that the significant drop here around 24th of January. That's the date when Wuhan was locked down. And compared to what we have 2019, the same time. So we actually trying to synchronize the Chinese New Year day. So the 2019 figures are not exactly January 30, but it's actually synchronized with the Chinese New Year. And again, this is for outflow of from Wuhan. So people are actually moving out of Wuhan in 2019. So there's a huge volume of travelers, but this year you can see is almost zero. Okay, and then another important information, of course, another part of our data collection, obviously, would be the infection data. So basically we have, so it's very important to realize that we, later on I'll explain the model. So basically it is SEIR or SEICR model. So that should involve like number of infected individuals, number of recoverers, and so on. So in fact, what the sort of data that that is available basically only include number of infected cases, or strictly speaking, the number of confirmed cases. There are people who were not confirmed, but basically they're infected. And later on, I'll tell you how we deal with that situation, which is normally referred to as information loss or information latency. So here are two examples showing Beijing and Shenzhen. The number of infected cases, number of recovered cases, and death toll. So basically, we have all this information for 367 cities on a daily basis. And this is actually just, I have to emphasize that for Wuhan and quite a number of cities in Hubei. Hubei is the province of Wuhan. I'll show you later on when we do the where we did the data matching or the data fitting. Wuhan and quite a number of cities in the Hubei province did not seem to be consistent. So obviously, we suspect or we believe that Wuhan data is seriously underreported. So there could be a lot more cases. But the other cities like Shanghai and Guangzhou seems to be reasonably good. Okay, we extended the data collection to Korea, South Korea, Italy, Iran, Japan, and recently also to Australia and a few other countries. And basically we look at different provinces or states, or in the case of Japan, prefectures, they would like to call it. And then for Australia, we basically just look at different states like New South Wales, WA, Victoria, and so on. Now, as I mentioned, this is another serious problem with the modeling, delayed information, and also missing information. In very simple terms, basically what we are saying is the actual number of infected cases or infected individuals is bigger than the number of confirmed cases. That is the official number or official figures that we normally see from government or from the authorities. And it's actually a lot bigger, not just bigger, a lot bigger. what we are saying is the number of confirmed cases is certainly not the true number of infected individuals at any given time. So we are confronted with basically two issues here. The first one is people are actually moving in and out of the city. And so our model should be able or must be able to take into account especially infected individuals who are actually moving out of a particular city or into a particular city, okay? And the second issue, information loss. So we now know that in a typical like SIR model or SEIR model, the number of infected individuals are not always available. And in fact, the available data is usually the number of confirmed cases, which is not equal to the number of infected cases. So first of all, for the benefit of the audience who are not familiar with modeling or disease spreading model, so let me spend just a few minutes to explain the background. So we have a network of people here. And basically we assume that everyone here would assume either one of the four states, SEIR. So we'll start with, the entire population at the beginning. Everyone is susceptible to COVID-19, and then get infected, but not showing symptoms of that exposed state, and then infected, and then recovered or removed. So we basically put recovery and removal in the same group. So that's the standard. And then we have standard differential equation, trying to describe the transition from one stage to another. So there are a group of people in the being infected, and these people are able to infect others. So the differential equation basically take care of the transition from one state to another. And so this is actually the very standard differential equation. So you don't have to worry too much about the details here, but anyway, this beta, kappa, gamma, these are the rates or the parameters of the model, which is used to describe the different dynamics. Okay, so in some country, you will see the infection rate is particularly high. And in some country, for example, Japan, we found that in Japan, the infection rates are inherently low compared to USA and UK. Presumably because I think the Japanese people, normally they wear masks, face masks when they go out, even, not because of COVID-19, but it's very common. And social distancing, all this are, it could be inherent in some of the community. So these are the parameters. So infection rates, recovery rates, and eventual infection percentage, delta I, also are part of the parameters. And data, PI is the population, so we were able to collect PI from the internet. And II, RI, these are normally these are the two available pieces of information published. Note that we also have death tolls as well. So, but that is actually in the R group. Okay, so what we are doing here is we try to integrate the intercity travel data in this SEIR model. So what we are saying is that we basically divide the entire country or entire population into subgroups. So this one subgroup will represent, for example, one particular city or state. For instance, this is Perth, and this could be, or this is Western Australia, and this one is Victoria. So we have actually people moving in and out, you know, from stage to stage. So we use what we call a migration matrix, so intercity migration matrix or interstate migration matrix, to describe the intercity travel, the relative volume of people going in and out. For example, MIJ is basically the traffic going from city I to city J, and so on. Okay, and in our model, the diagonal elements, so M11, M22, and so on, are all set to 0. So in other words, we assume that people within a city is not traveling. So, or it doesn't really make sense. You know, it's going from this city to the same city. Anyway, we have this migration matrix, and we'll be able to use this migration matrix, which is actually, the actual values are actually derived from the, in the case of China, from the Baidu migration. So that's the Baidu migration strength, MIJ. For example, I is Wuhan, J is Beijing. So we've got MIJ over here from Wuhan to Beijing. And this is actually the term contributing to the daily increase in the number of infected cases. So this is actually saying, the number of people moving, the number of infected individuals moving from I to J, moving from city I to city J. And again, we have in and out. And we made also a couple of assumptions in the model. We assume that the people who are infected will not move, or so we just ignore the movement of infected individuals. So presumably they will stay in hospital, or they'll be quarantined. And recovered individuals, again, assumed not to move or stay in the same city, at least for a certain period of time, even after they recover. And so it's also very important that the parameters are specific to a particular city or a particular region or state. So when we do the simulation, basically we assume each city has its own set of parameters, different from another city. So, so you can imagine we have quite a big set of parameters. For Australia, for example, we have one set of parameters for Victoria, another set of parameters for Western Australia, and so on. So we have, you know, a few sets of parameters, and then we have to run the simulation together because we are trying to incorporate the movement of people from one stage to another stage. So this is actually a travel data integrated SEICR model, which is the first step. And you will see, apart from the usual alpha, beta, gamma, these are the parameters characterizing the transmission dynamics of that particular city, J, or state or region. In addition, we have a travel migration matrix, MIJ. So here you will see the original SEICR model has been augmented with this additional terms corresponding to the migration data. So that's the first step. The migration matrix also affects the population change. And because people are moving from one city to another or from one stage to another, the population of a particular city or particular state will actually change. So that has to be taken care of. So now we have basically a set of parameters, and the differential equation. The differential equation is the dynamic system with a number of parameters. And note that these parameters are unknown. They are not known. So our job is to try to compute or estimate these parameters, all these parameters. So suppose we are trying to simulate the entire China, then we have 367 cities, all the parameters. So we have 367 sets of parameters, all different, and with the migration matrices as well. And then we are trying to estimate the values of each of these parameters from the historical data. So what we are doing here is, what we are dealing with here is a constrained nonlinear optimization problem, to be exact. So we've got the data, okay? So these points are the data. And the curve is supposed to be generated by the model. That's the differential equation. Okay, and the differential equation has a set of parameters. And our job is to try to estimate the set of parameters or the values of those parameters that would minimize the errors between the actual data and the generated trajectory. So that's our job. And it turns out to be a very hard, very difficult problem, because this is actually a nonlinear optimization problem. We set up, the tool that we use in our estimation is basically a evolutionary algorithm. It's a kind of a genetic algorithm. So we start with a certain initial guess, and then we iterate until we find the minimum mean square error. So basically, that's the idea. So the model will generate the solution, which is compared with the actual historical data. Oh, one more thing. Note that not only the parameters are unknown. In fact, we have a few more unknowns corresponding to the states of the system, namely ET, which is the number of exposed people, and so this has to be estimated as well. So this ET is not available from the data. So the data only provide I and R, but there's no E. So the curve down here is actually our estimated number of E. Okay, so in other words, the data fitting not just to estimate the parameters, but also the unknown states as well. Okay, so let's look at some of the results that we generated back in February 17. So this are the first set of results that we completed back in February for 367 cities in China. You see, this is the estimated number of exposed individuals. And then we have the estimated I, that's the number of infected cases, and then the actual data here. So I haven't actually, let me just see, I don't have Wuhan here. The reason is that the Wuhan data, the error is very large for Wuhan. So we are not able to get reasonable match for the Wuhan case. So our understanding is that in the early outbreak in Wuhan, there could be underreported. So the number may not be the actual official number or figures may not be so reliable. So and so were some of the data in the same province. Okay, and so we are able to actually make predictions then. Now we have a set of parameters. So okay, let me just go back. So we've got the parameters from the data fitting procedure, which is a constrained nonlinear optimization problem. So once we have got the parameters, we are basically able to generate the trajectory or the solution with that set of parameters. And then with the same set of parameters, assuming everything remains unchanged, okay? So we assume that the parameters will stay unchanged for the next 1 or 2 months, and we can actually extend the solution to future points. So this is the prediction curve here, all the way until the middle of July. So that was actually performed. So these predictions were performed on February 17. And you can see the peaks are all around March or late February, okay? And these are actually quite consistent with the actual data later on we collected. And we are able actually to perform some analysis at that time. For example, looking at the statistics of the peak times, roughly clusters around late February, and some cities actually had peak in the middle of March and late March as well. Now, notice that these are the first wave, and in fact, you will see typically, let me just refer back to some of these figures here. It's actually quite typical that at the beginning, so you will see here, let me just go back. Oh, sorry, I missed out. Okay, anyway, let's say Shanghai here. If you project this curve back to like 1 or 2 weeks, you would typically see there are infected cases, but relatively small number of infected cases for about 1 or 2 weeks. And typically you will see the number of infected cases maybe less than 50 for 2 or 3 weeks. And then you will see a significant increase. Usually it comes very rapid rate, and then the peak in around 3 to 4 weeks. Okay, so this is like a very typical sort of profile. My understanding is that the initial 2 weeks of very, very small numbers, basically during that time, people are usually unaware of the outbreak until probably there are some emergency situations from the hospital or in the community. Then people started to realize, or the authorities started to realize, that there is an outbreak. And then certain intervention would be implemented, and then the outbreak would then subside within like 2 or 3 weeks. So it's fairly typical sort of profile. Okay, so let me just continue with, so we are able to actually perform some analysis for China. For instance, looking at the distribution, number of infected individuals in different provinces, cities, and we are also able to construct a database. So we now have something like a few hundreds of sets of parameters corresponding to different propagation profiles or different progression profiles. And the first set of data are basically from China. And we collected between January and April. And what we have done here is we're trying to build that database of parameters and use that database to perform prediction. So we assume that in the case of like Italy, Iran, and Korea, these 3 particular countries, we are trying to match the early outbreak data with the data that we have from the 367 cities in China. And then we are using a data-driven model, basically, picking the best or the nearest candidate sets, which produce profiles which is similar or nearest to the available data collected for the early outbreak. And we use this approach to perform prediction for Italy. It turns out to be quite consistent with the real situation, and these are the results for South Korea, completed on the 8th of March and then updated on 17th of May. Note that this kind of data-driven prediction would be more accurate if we have a bigger set of data. So in other words, we assume that the database that we have, I mean, the different sets of parameters will be able to cover different transmission characteristics, contact topologies, and so on. So we are trying to do prediction based on historical data. So that's one application up to this point. So we've got predictions for South Korea, Italy, and Iran based on this particular approach. Okay, so the next challenge, the loss of information, and I'll explain in the next 10 minutes how we deal with this problem. So we mentioned earlier that the number of infected cases, this is the actual number of infected cases, the actual number, is a lot bigger than the official figures. That C refers to the number of confirmed cases. So what we are saying is SEICR, that's the usual state transition, but we create one more state here, C. So what we are saying here is the group of infected individuals, only some of them, not all of them, maybe 20% or 30% of these people will be tested and then confirmed or tested positive and hence confirmed as COVID-19 patients. But there could be still a large group of infected individuals who have not been tested. And in fact, our latest work, which we completed last week, using a similar model, have shown that the C to I ratio is about 0.23. So unconfirmed to confirm is about 3.3 to 1. So in other words, there are about 3 times more people who are actually infected, but not confirmed. So that transpires a very serious problem. The testing capacity of a particular country or particular city will be quite crucial to the containment of the virus. The reason is that we have now been confirmed that the transmission of COVID-19 is actually possible through asymptomatic patients. That is, people who basically are contracted, but they have no symptoms. So they just like normal people, but in fact, they are able to infect other people. So that has become a very serious issue. And so what we are doing, basically, we introduce this additional states. Now, you can imagine, early on, I mentioned that E is unknown. We only have I and R as historical data or as available data. Now, C is now an additional state which we do not know let me just repeat again. I is unknown, but C is known. So we've got C and R. Okay, C is the official data. R is also from the official source. But E is not known. I is also unknown. So we actually introduce one additional state, C, but C is the actual available, the C can be derived from the actual available data, but I is unknown. So we then modified the original SEIR model, and now we have the SEICR model with C being confirmed, which will replace I in terms of the available data. And here I would also like to introduce an additional term. I'm sorry about this, the algebra, it's a little bit complicated, but please don't worry about it. Basically, it's just SEIR, the state transition equations. But I would just like to draw your attention to this particular additional term, KJ, which we deliberately introduced here to assess the level of active intervention. So, for example, social distancing, or some sort of non-pharmaceutical control measures could actually be modeled here by an additional term. So basically what we are saying here is that we assume that every infected person will eventually lead to KJ number of additional eventual infected individuals. So basically this is an indicator of the level of intervention. So what we are saying is that if KJ is large, then, so KJ basically is the increase in the number of eventual infected individuals for every additional infected person. So if KJ is large, that means the intervention level is very low, or basically there's no intervention. So suppose the government actually implemented very stringent measures, then KJ is supposed to be very small. So by adjusting the value of KJ, we are able to understand how effective, or we are able to assess the effectiveness of particular intervention implementation. So this is a full set of parameters for our models. Now we have one more stage, SEICR, and also again we have the migration matrix, MIJ, and also the level of intervention. So the infection rate remains the same. So we still have alpha, beta, and gamma, which is the basic transmission characteristics of the system. And then we have the additional term for intervention, for assessing intervention. And this is basically what we are doing here. So we've got SEIR model for one particular area, one particular region or state or city. And then we have the MIJ matrix to describe the movement of people, from in and out of a particular region or particular city or particular state. Okay, then this is basically this is our model, and we have recently worked on Japan. So 46 prefectures in Japan. And it turns out that what we are interested here is to estimate. As I said, now C can be derived from the model, but I remains unknown, as well as E being unknown. So, with the optimization procedure, we estimated the best set of parameters, and then estimate the number of infected individuals. And it turns out that this one was performed, I think, before the end of June, okay. And for Japan, we found, basically, the model actually found that the number of infected individuals is about 20 times bigger than the number of confirmed individuals. Quite significant. In fact, that actually is quite consistent with the total number of COVID-19 tests performed in Japan, which is one of the lowest in the world for some reason. So these are the statistics of C to I ratio, and this is the eventual number of infected people under different levels of control. As I explained earlier, the K, the parameter K earlier, so I spoke about this one, so that's K, can actually be adjusted in the model. So we'll be able to see the extent or the scope of the outbreak for different values of K. So when K is bigger, that is corresponding to a much less control or a very low level of intervention. You will see the number of infection cases will be a lot bigger. For the United States, we actually have done the US, actually, this one was also completed end of June. The number of infected individuals was about 5 times bigger, 5-fold as many as the confirmed number. So, and in fact, I mentioned earlier, the results that we've got last week from Australia, Canada, Spain, UK, Italy, South Korea, the average value is 3.309. So that is roughly the sort of average number. Okay. And as I said, by adjusting the parameters, we have 2 different set of parameters. One is the inherent infection rates. That's the alpha, beta, and gamma. That's the infection rate, recovery rate, and so on. And then we also have the KJ, which is the parameters corresponding to the different level of intervention. And we can actually compare the effectiveness of applying intervention and also the effectiveness of actually changing the inherent infection rates. For example, here for Japan, it's quite interesting to compare to 2 different countries. And it turns out that for Japan, active intervention is a lot more important because the inherent infection rates are already quite low. This is actually from the model. So by fitting the data, we basically find that the Japanese data shows a comparatively low values of alpha and beta. That's the infection rates inherently much lower than the case of USA. And active intervention would be actually more important. But in the case of USA, you will see the inherent infection rates are relatively higher compared to Japan. So there's still quite some room for improving the situation by maintaining personal hygiene or mask wearing and raising the level of vigilance compared to changing the value of K, which is not as effective as, so obviously the reason would be from the modeling point of view is that the United States has a apparently higher or inherently higher values of infection rates. Okay, so I have a few more minutes to look at just to do a conclusion. The good news is that effectiveness of medical treatment seems to be improving, and so the recovery rate will increase in time, and making the decline rate much more rapid. So you see the typical curve is actually contributed by all these different parameters, And for example, if gamma, which is the recovery rate, is bigger, you will see the decline is much more faster than, you know, the case when gamma is smaller. Okay, and another thing that is important is so far the model actually is able to produce the progression profiles, you know, with typical alpha, beta, and gamma, and you will see that the typical profile is like, you know, a bell-shaped sort of curve. So it goes up, and then within a couple of weeks it will go down, assuming that people are complying with the social distancing rules and things like that. But you will see the borders remains open, practically open. People are still flying around, and we cannot rule out the possibility of a second wave or third wave. And in fact, this is actually happening now. As I have shown you earlier, in Hong Kong, we are now having the third wave of outbreak. So we have to tighten all the control measures like social distancing rules and so on. Okay, conclusion. We mentioned about the model, and you will see it actually has, the model is based on single population, and then we extended it to multiple populations by introducing an intercity migration. So basically we incorporate the intercity migration data to extend the single population model to a multiple populations model. And then we introduce different parameters so that we are able to assess, for example, social distancing rules, the effectiveness of active intervention and so on. However, at the moment, personally, I would see there's a danger of third or even fourth waves of outbreaks. The reason is the invisible infectious hosts that actually exists due to asymptomatic transmission. That is, people who do not have symptoms, but is actually infecting other people. And we have shown in our study just a week ago that if we are able to increase the testing capacity, so one of the ways to solve this problem is that we increase the testing capacity drastically. So we're trying to test almost everyone. Then we'll be able to identify the invisible ones. Okay, and our simulation basically shows that if we increase the testing capacity by 10 times, so 10-fold bigger, it's like almost like a mass testing sort of exercise, we will be able to reduce the number of infected cases by 50%. So if we increase 10 times the testing capacity, we have, you know, we have almost like only half of the infected cases. And at the moment, the confirmed cases only 23% of the total of the actual number of infected cases. That's our estimation. So with that, I think I would just end by saying I think mass testing will be one of the possible way to go forward. Okay, so these are the references, and I think I'll stop here and take questions. Okay.
Thank you very much.
Okay. I can't hear anything. So.
Can you hear us, Mike? Can you hear us now?
Yes. Now, yes. Yes.
Okay. So this is Michael here. I was a bit confused by your confirmed category is the data that you see. They are the actual infections that you identify, correct?
Yep.
And the removed category is also data that you see.
Right. Correct. Including death tolls.
including death tolls. But this includes the infected ones that you don't see, right? But you identify them when they become removed.
Oh, yeah. I have to apologize that the one that I have shown you, remember, can I just bring up this? Okay. All right. Just a moment.
Yeah.
Am I sharing it? Nope, not yet.
Yes, it's just started sharing. Yeah.
Okay. Okay. Referring to this diagram here, I apologize that that was the model that we used a few months ago. But you can imagine this R should be split into two different R's. One is RU, and then this will goes to RC.
Yeah. Okay.
So we have to estimate one more unknown state, in other words. So that is our latest model. So I have to sort of modify. So this diagram is not exactly correct in the sense that there are confirmed people who then goes to R, but there are people who are not confirmed, so unidentified, but they still recover, right? And these numbers are not the official numbers. You know what I mean?
Yeah, there's ones that never appear officially at all.
Right. So yeah, exactly. So the official data that we have from the authorities will be the RC, which is the recovered person who were confirmed earlier. But there's still quite a large group of people who are RU, R subscript U, which is the unconfirmed one or the unidentified one. Yeah, then it makes the it will make the estimation procedure a lot more difficult, because when you have more parameters, more unknowns, it's actually more difficult to converge.
Yeah.
I mean the algorithm, right?
So I have another separate question. Where do you get the mobility data for not China? Because presumably you don't have data.
Right. Actually, the Transportation Bureau, for example, Japan, the e-government, the Japan, something like egovernment.com, something in Japan, they actually published data for, I mean, they're basically traffic data. So we estimate those numbers from those data. In the case of United States, they actually have monthly data showing people moving from one state to California to Arizona, for example. But again, it is not a data. In many countries, the data available are not daily data. They could be weekly data or monthly data. And some data are not very detailed. I mean, in a way, it's very crude. But we can just base on those. So for migration data, I admit that they are not exact. They're only indicative.
Yeah. Okay.
Comment on the splitting of the R. Maybe you need to repeat the question. There are historical cases that are sometimes popping up depending on.
Sorry.
I'll repeat the question for you, Michael.
Oh, sorry. Yeah. Okay.
Maybe they help estimating also the invisible R that comes from the eye, and therefore correct the ratio of I over C.
So the question is about historical cases that originally were not confirmed, but you found out about them later on. So the cases that you find out, like after they've already been recovered, you test them and you find out that actually they were infected. Can you feed them back into the model? Right.
Yes, they are considered as C, not I.
Okay, so you basically post-fit them to the model once you know.
Right. In fact, so far we are using. In fact, there are two sets of data when we look at the usual format. They usually have so-called onsets, so they're not confirmed, but there's like a 10 days delay between the two different types of data. The one that we the one that we have used in our work is the one that are confirmed infected cases.
Yep.
So to answer that question, I think, for example, today we only have the daily confirmed data, so that would correspond to, we don't care with the history. I mean, that particular person could maybe unidentified a week ago, but if it is confirmed today, then it will still be considered as confirmed.
Yeah. So what was the problem with Hubei province? You mentioned that the data for cities in Hubei was not so good. Was it just that it didn't fit the model very well, like Wuhan, or was there some systematic?
Right. Yes. For example, when we are dealing with matching. So basically, yeah, here, we perform, well, one of the good things about doing this multiple population or multiple cities model is that Wuhan will be just one out of the 367. So we are actually combining the errors, I mean, all the mean square error together. So then we try to optimize the optimization basically based on the criteria that the overall error is minimum. So it turns out that when we have stopped the simulation, so in fact we performed every time 500 simulation runs. So among the 500, so we pick, you know, the best 10 candidate set, and then we examine, you know, the individual errors. And it turns out that almost every time we'll see among the 367 different set of parameters corresponding to the 367 cities, Wuhan and a few other cities in the Hubei province, within the Hubei province, were not able to converge to any reasonable, you know, parameters. So the one that we have got, then we provide the simulation. We found that the trajectory is a lot higher than the data. So the error basically is very big. I mean, for that few cities in Hubei province, but we can't do anything about it. And for the rest, like 300 cities, the errors remains very small. So I mean, the set of parameters that we have estimated and then used in generating the curve, that those curves are reasonably close to the data, except, you know, for the few cities in Hubei. So yeah.
Okay, thank you.
Do you have any questions from our online participants? Jack, just send a question.
Jack sent a question. Okay, so can you see Michael, can you see the question from Jack in the chat?
Ah, okay. Let me turn on the chat. Okay. What is it? Okay.
So it's about missing cities basically, and people entering from missing cities. I guess I would have a related question.
What do you mean by missing cities?
So other cities that are not, well,
okay. All right.
Cities, or in Australia, importation from overseas.
All right. Okay. I don't have a good answer for that. In fact, our model, we are still struggling with international travel data. In fact, ever since I think starting from March, the traffic volume has already been very, very small. I mean, international travel. But there are a fair bit of intercity travel within one country. You mentioned about missing city. My understanding is that the question is referring to the situation when there is no data showing the indicative travel volume between one particular city. Is that right? Or
I guess that's what he's getting at. Yeah. So
yeah, right. I would presume. I mean, for the case of the China study that I presented earlier, the 367 cities were the cities that we have identified from Baidu migration data, which has the highest travel volume. I mean, travel data. That is to say, because there are more than 367 cities, obviously, in China, but the one that we did not include were the ones that basically have quite insignificant, number of travelers. So that's the reason why we did not include it. But yeah, obviously that will be a problem. I mean, when you miss a city or miss some cities, and there will be imbalance in the number because people going into into somewhere that is not accounted for. I mean, then presumably if the migration strength is not very high, then the error is still tolerable. Right.
did that get your question,
Yeah.
Jack?
I'm not sure if I answered the question.
Oh, no, you did. Thank you very well. I suppose I was also slightly curious about whether it might be useful to have a sort of additional node, which sort of represented all the rest of the world.
Right. Yeah. You're quite right. So you could create an artificial node corresponds to like a black hole. I mean that will account for all the differences. Yeah, you can do that. Yes. Right.
All right. Thank you.
Okay, no more questions. Let's thank Professor Xi again for his interesting talk.
All right. Thank you very much.
Thanks, Michael.
All right. Thank you.